Okay, section 8.2 is kind of going to continue an idea that we've done before about area under the curve, but instead of doing area under the curve, we're going to do area between two curves. So quick little review. We've done lots of problems like this, right? Find the area under the curve between the x-axis, y equals x squared from 0 to 6. So I could draw a little picture here. Y equals x squared from 0 to 6. So we're just going to integrate from 0 to 6 of x squared dx, right? That's how we're going to find that area under the curve. All right. So it's a little review because what we're about to do is find the area between two curves. And there's going to be two ways to look at it. One is by just using the shapes and subtracting the areas per se, which you'll see in a second, versus drawing a little picture and using rectangles, which we're going to do also. So a little theorem. If f and g are continuous, and f is always greater than g for every x in some interval from a to b. While you write that down, I'm going to draw a little picture here. We got this one little curve here we're going to call f of x. Got another little curve here we'll call g of x. And we'll call this a, and we'll call this b. It's important to realize that f is always on top. If they switch, where the other curve goes on top, we're just going to have to flip-flop what we do. The theorem says that in order to find the area between those two curves, we're just going to integrate f of x minus g of x. And if you think logically about this, it should make sense. Watch the little color here. That if I were to shade in all of that, that's just the integral of f of x, right, from a to b. So then if I change colors here and shade this, that's the integral of g of x from a to b. If I subtract those two, I'm going to get the area I want, right? So that's kind of the way to look at it in terms of how we do it. We also like to think that what I'm about to show you might seem a little bit weird. You might not know why I'm doing this, but it will clear up as we go through the chapter because we're going to use this idea a lot. Is kind of back to Riemann sums. There's my f, there's my g. If I think about a rectangle right here, we're going to add up all the rectangles. So what I do is draw what I call a typical rectangle in there. Okay. And what I do is I find the area of that one rectangle. Remember, there's like infinitely many of these though, right? Like Riemann sums. So notice the height of that rectangle. This is the height times the width, right? So notice the height of that rectangle is just f of x minus g of x. So that is the height of that rectangle. And then the width of that rectangle, we're going to call like delta x or dx. So if we think about the fact, and then the integral adds up. Remember, Riemann sums is an integral. Remember, if we go way back to the beginning of Riemann sums, the definition of that symbol was the Riemann sum, right? Adding up rectangles. So this just says add up a bunch of rectangles. This is the width, the height, and this is the width. Okay, I'm going to do some examples. So we'll see. One thing I want to do before I do some examples is talk about negative areas. Sometimes people are bothered when maybe the curves are underneath f and g, but remember this. It doesn't matter where these curves are. This will always work. You just got to know which one's on top. So if they switch, you have to know where they switch, and we'll have to do two different integrals. You'll see those in my examples. But think about this. If that's just f, this is a negative area, right? That purple area would be a negative area. If I just integrated f from a to b, it would give me a negative answer. We've learned that that's how that integral works. But then you throw the g in here also, it's going to give you that negative area, right? The red area. So we're going to get a purple number, which is negative, minus another negative number. But remember, this negative number is going to be bigger. So it's really going to be like plus, and you're going to wind up with that positive area, which is exactly what you want. Okay. So what I have now is 4 examples. I'm going to do all 4. You can feel free to turn the video off at any time if you feel like you got to know what's going on. But there's little twists and turns in all of them. And plus, I didn't talk at all about switching a graph sideways, which we're going to look at in a couple of the problems. Okay, so I might say maybe fast forward if you think they're easy ones, but the 3rd and 4th example are actually quite different because they're going to be sideways. So here's what you're going to do in all these problems. First, draw a picture. Most of them are going to be pretty simple. They don't have to be great pictures. There's y equals x squared. There's y equals root x. We're trying to find the region bounded by these 2 graphs. So we're trying to find this area right there. So every time I do one of these problems, and you might not want to do this, but you should, because it's going to be important when we start taking the shape and revolving it and making a 3-dimensional shape. It's going to be a lot easier to visualize. So what we're going to do is we're going to add up all of those rectangles, okay? All of those purple rectangles, okay? I know you can just do f minus g. I get it. You know, you could just go, hey, Mr. McGurk just said, look, there's my top curve is the root x minus the bottom curve. Done. And it's right. But in terms of the bigger picture and where we're headed, it's probably not best to think about it that way. It's probably best to think about the rectangles, because those rectangles, like I said, they are going to get revolved later on and make 3-dimensional shapes, and you kind of need to be able to visualize that. So what is this? This is the height of the rectangle. Top curve minus bottom curve in essence. That's the height of the rectangle, and this is the width. And my limits of integration are from here to here. So I need to find those points. I'm going to add up all of these rectangles. Think about there's infinitely many of them in here, right? So the way I'm going to find those is set these 2 equal to each other and just solve a little algebra equation. Some equations are easier than others. This is pretty easy. I guess you could square both sides. You get x to the 4th equals x. You could also probably just do it in your head. It's going to be 0 and 1, right? X equals 0 and x equals 1. So in order to save time, I'm actually going to stop there. I'm hoping you can do the integration itself. Okay, they're just power rules. Most of the integration is going to be really simple. There's going to be a lot of power rules, but I hate to waste your time walking through and doing all those. And even in the homework, to be honest with you, if you just kind of left it like this, I'd probably say fine, because that's the concept for this chapter. I'm going to need you to integrate it ultimately, because that's how we're going to get our answers. Easier for me to check if it's just a number. But you can save some time in the homework. So next one, I'm going to rewrite here so I can see it. Sorry, y equals y plus x squared equals 6. Y plus 2x minus 3 equals 0. All right, so I'm going to rewrite these into forms that just help me graph it. And I need the 2 functions anyway. So the first one is negative x squared plus 6, and then negative 2x plus 3. So an upside down parabola up 6 units. And then negative 2x plus 3 is 1, 2, 3, has a slope of 2. I want to be a little bit careful. A lot of times you can just draw the pictures really quick, but you got to be a little bit careful of intersection points. Sorry, this is up here at 6. 3 negative slope. So something like this. My picture might not be to scale. It's not super important. What it does tell me is which one's on top, right? There's my rectangle. The height of that rectangle is that top curve, which is right there, which is the negative x squared plus 6, minus the bottom curve, which is negative 2x plus 3. That's the height of the rectangle, multiplied by dx, which is the width of that rectangle. And I just need those limits of integration. So I'm going to set negative x squared plus 6 equal to negative 2x plus 3. Gives me x squared minus 2x. I'm bringing everything to the right side. X squared minus 2x minus 3 equals 0. Factor. Usually they come out nice for sure. X minus 3x plus 1. So it looks like negative 1 and 3. Negative 1 and 3. Again, I'm going to stop there because it's just power rules. You can simplify anything in there first. I like to just leave it like that so we can see it. This is like my f minus my g, right? F minus my g. All right, we're going to turn them a little bit here now. The next one, actually, I'll just write it down here so you guys can see it. The next one is y minus x equals 6. Y minus x cubed equals 0. And we got a third curve, 2y plus x equals 0. I told you there'd be some other stuff going on. Again, I'm going to rewrite them. Y equals x plus 6. Y equals x cubed. Y equals negative 1/2 x. So what's going to happen is we're going to get different regions now. So if I graph these, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. That was fun, wasn't it? 6, 0, or 0, 6, sorry, for one point, and then negative 6, 0 for the other one. So there's my y equals x plus 6. Okay. Y equals x cubed. Looks like that. And y equals negative 1/2 x, just really roughly is something like that. So you can see I have 3 regions now, or not 3 regions. I got 3 curves that are breaking up my region. But notice, here's where it gets a little bit weird. Notice my rectangles here. Like, which is the top curve and which is the bottom curve? Well, if I draw my rectangle right there, it's a line on the top and the line on the bottom. But if I draw my rectangle over here, notice it's the line on the top with the cubic on the bottom. So I'm going to have to treat these as 2 different problems. And the break is right here, right? It changes right there. This is why these rectangles are pretty important, so you can visualize that a little bit. So first of all, I need to find all these intersection points. Clearly, this one's 0, 0. They're pretty quick to find. This one's going to be 2, 8, x cubed, 2, 8. 2 plus 6 is 8. This one's not quite as obvious. I'm just going to do a little quick math. Negative 1/2 x equals x plus 6. You just find the 2 curves that you're trying to intersect. If I, let's see, bring this x over here, it's 3/2 x equals negative 6. So times 2/3 is negative 4. So this one is negative 4 something. It doesn't really matter what. It's negative 4, 2. So notice now this little area here is that first rectangle, which is the x plus 6 curve on the top, minus the other line, which is the negative 1/2 x on the bottom. And that one's going to integrate from negative 4 to 0. And then I'm going to add to that, whoops, a little dx there, sorry. I'm going to add to that the other integral, which has the x plus 6 on the top also, but this time on the bottom, the minus is the cubic. And this one we're integrating from 0 to 2. And again, just power rules at this point, right? Just power rules. All right, so the one little twist, that was one twist where you got 3 curves that are making 2 different rectangles. You got to know which curve's on the top and which curve's on the bottom. And the last one, I'll throw another wrench at you here, is instead of being y equals, it's x equals. Okay, so let me show you how this works. Now, this is x equals y squared, which is this curve. And then this one is x equals 2y squared minus 4. So it's going to drop down 4. It's also a negative. Oops. 2, sorry, did I do that right? No, I didn't do that right. No, x equals, yeah, that's right, 2y squared minus 4. Drawing a blank on my picture. Hang on a second, sorry. We're going to go 2y squared, so x is... I want to make sure I slide this the right way. It's a right side out. Here we go. There we go. So we're going to go 4 units that way. Sorry, I drew a blank on that. 4 units that way, but then it's looks like this. It's a little bit more, it's steeper because of the 2 instead of the 4. So there's my picture. So notice now everything's sideways. You actually have a choice in all of these problems. You can draw your rectangles any direction you want. You can draw them vertically or you can draw them horizontally. If you draw them vertically, you have to have dx's. If you draw them horizontally, you have to have dy's because now you're with this turn. So it's dy, which means if you draw them vertically, everything's in terms of x. If you draw them horizontally, everything's in terms of y. It's your choice. We'll talk more in class about how I know which ones to do which ones. I'm going to just do this one in y just because it's different. It's probably easier anyway. I'll talk more in class about why I choose one versus the other, like how I dictate that a little bit. Just remember, it's easier to pick dy's because everything in terms of y, everything's already in terms of y, right? So if I did it the other way, I'd have to solve these equations for y. Not the worst thing in the world, but I'd have to do that. And now instead of the top minus the bottom for the height of the rectangle, the height of the rectangle is actually the right minus the left. So the right curve in this case is the y squared minus the left curve, which is the 2y squared minus 4. It's dy because the width of the rectangle is dy. It's horizontal. Now I need the limits. So again, remember my limits need to be in terms of y, not x. Once you decide which variable, and we'll talk more in class about how I decide, once you pick a variable, you got to stick with it. So everything needs to be in terms of the variable, the dy or the dx, the y is in your equation, the x in your equation, and then your limits. So we're going to go, y squared equals 2y squared minus 4, which means y squared equals 4. So you get, plus or minus 2, negative 2 to 2. Here's your negative 2. Here's your 2. And again, really easy power rules. So hopefully that's enough examples. I will talk more in class about the x versus y issue, and we'll go from there. Let me know if you have questions.